I think we can start now. So first, I want to present myself. So I'm Faten Driss. I'm a technical advisor at RatedPower. I will be your panelist today. And I'm a renewable energy engineer and a part of the customer success team. So let's dive into our webinar. So today objectives are, first, we are going to talk about the importance of probabilistic analysis. And in the solar energy field, we will explore why probabilistic analysis is crucial for obtaining accurate energy results, and by leveraging pvDesign built-in probabilistic analysis capabilities, we will be able to gain more realistic assessment of our project. After, we are going to talk about the calculation of the percentiles, and we will also talk about the incorporating of uncertainty, the importance of uncertainties, and I'm going also to show a project that is already created in pvDesign. We'll have also a conclusion part, and if you have any question, everything will be answered during the Q&A section. So let's first start by presenting our tool, pvDesign. So pvDesign is a cloud-based software that allows you to pre-dimension your utility scale ground-mounted PV solar plant, and it provides you an optimized it can help you to optimize your PV plant system, including a probabilistic study component. So with pvDesign, users can efficiently plan, simulate, and analyze PV projects of various scales and complexity while considering the uncertainties associated with solar resources data and energy yield estimates. So by integrating probabilistic analysis into the design process in pvDesign, it will enable the user to account for factors such as the weather variability, equipment performance degradation, and providing more realistic and comprehensive evaluation of project risks and uncertainties. So the probabilistic approach empowers users to make informed decisions, optimize system designs, and mitigate potential financial and energy yield risks. So we will start with the first part of our webinar, which is the importance of probabilistic analysis. So this analysis will play an important role in solar energy projects by providing more accurate and comprehensive understanding of potential energy yields. It also acknowledges and quantifies the inherent uncertainties associated with the solar energy generation. Also, by the probabilistic analysis allows project developers to assess project performance under different scenarios, identify potential risk, and optimize project parameters to maximize energy production. So with pvDesign, participants can explore a wide range of input combination and generate probabilistic energy yield estimates that accurately represent the project performance in a real condition. So it also allows the developers to align their expectation with the uncertainties of solar energy generation and ensure their projects are financially viable, technically feasible, and capable of delivering the expected returns. So the ability to make a well-informed decision. So let's start to talk about the calculation of these percentiles. But before diving into the uncertainties that we will tackle in the next section. So calculating energy yield estimates using statistical percentiles like P75, P90, P95, and P99 is made easier with pvDesign. So when you create a project, a design in the software, an energy yield calculation for you is done. It calculates how much energy your PV plant will produce during its lifespan. The first energy result that you will have, it will be the energy result of the first year of the operation of your plant. So when you calculate the energy yield for simplicity and statistical analysis, we assume that the weather values are distributed in a normal distribution, a bell-shaped curve. So this is a common simplification used in the most energy models. So the statistical analysis is identified with a parameter indicating the confidence level. The parameters are the P50, P90, and other percentiles, which are the probabilistic values. So our model in pvDesign will calculate your energy yield using the TMY file that you input when you input your meteo data file. So this TMY should be considered as an average and thus corresponding to the P15. So TMY corresponds to typical meteorological year. It's a set of representative values of any given meteorological parameter for any given location. So if the data is a representative of an average of over several years, the simulation results in considering as an average and corresponds to the P15 of and will be the mean value of the Gaussian distribution. So the P15 also corresponds to the annual production level that is expected to be exceeded with 50% of probability. It is the same for the other percentiles. If we take P75, for example, it will correspond to the energy of production at the 75th percentile, meaning that 75% of the data will fall below that value, and the definition will apply to the other percentiles. So also P15 is considered as a best estimate, but in some cases we can need other restrictive estimate like the P90, P99, which are conservative estimate. Usually this value is requested for financial purposes, for example when studying a debt, studying the depth structure. So you can see here the user can introduce the standard deviation in the simulation in the energy tab. So also while explaining the percentiles, you need to understand the difference between the p-value and the probability. So p-value, which is the probability of exceedance, this value indicates the probability that certain energy production level will be exceeded in a given year, and the probability indicates probability that the energy production level will be less than the certain energy production level. So if we take here the example of the P19, so the p-value will be P90 value will be 90% probability that 55 gigawatt hour annual production will be exceeded, and the probability will be 10% probability that annual production will be less than 55 gigawatt hour. So the p-value and the probability are interconnected. The p-value is 1 minus probability. So now you can ask like, what are the formula that are used in pvDesign? So it is following the Gaussian distribution, the normal distribution. So here you will have the formula for the uncertainties, and using the formula of the uncertainties, you will have the p-values based on the standard deviation input that the user enter inside the design process in pvDesign. Also, you can ask yourself, what are these values? So these values are known as the z-score values. So the z-score measures the distance between the data point and the mean using standard deviation. So we can take the example of the P90. So we can see the area will correspond to 0.9. So in this z-score table, you will see the areas here. So for the P19, it is 0.9. So this is the closest value for 0.9. You have 1.2 here and 0.8, and you will have the value corresponding to the P90 uncertainty and the z-score here. It is the same for all the percentiles. So now that we have seen how the probability values are are calculated, we need to talk about the uncertainty, which is the most important part, and how incorporating uncertainty is really important in the probabilistic analysis. So probabilistic yield estimation is a key feature in pvDesign. It involves statistical analysis to quantify the effect of the uncertainties on energy production over several years. So it takes into account various sources of uncertainty, such as the meteorological data, equipment performance, long-term degradation. So these uncertainties are quantified using the standard deviation sigma value that you can enter in pvDesign, which represents the expected annual variability. And the annual variability sigma value will be dominated by the meteo year-to-year variability. So you can see here we have the inter-annual variability, which is the meteorological conditions that vary from year to year. We have also the uncertainty of the energy simulation model that englobes the equipment performance estimation, losses due to shading, soiling, and other sources. And also we have the meteorological data, which the uncertainty of calculating the global horizontal irradiance, GHI. So this the standard deviation that you enter in pvDesign will encompasses various sources of uncertainty in the energy yield calculation. So let's see inside pvDesign where to input these uncertainties. So here we have the example that I will show, explain also after. When you clone the design and you are inside the design process, you can enter your meteo file in this section, and also you can see here the global irradiance value, the difference value from different sources. The user also is allowed to input the minimum historical temperature in this section. For the equipment, you can select your own equipment in this section, and also based on the manufacturer, you can have the efficiency. In the detail here, you can see the efficiency of your PV model and the equipment. So the most important section for the degradation and uncertainties, it's in the energy tab. First, here you can enter in the simulation your inter-annual variability, the sigma value, but also you can select the albedo that is a source of uncertainty. In the PV model losses, you have the first year degradation, the yearly degradation, also the bifacial mismatch. So you can enter this value here. You have also the soiling losses, and all the parameter will be considered in the uncertainties. So once you have entered all the parameters that you need, you have to generate your design, and as an output for the uncertainties value. So here you can see, as I mentioned in the beginning of the webinar, the first energy value that you will have here is for the first year, and the output will be in the energy yield report and the energy yield results, where you can find your probabilistic yield estimation and all the percentiles calculated with in pvDesign. So for our second part inside the fourth section of the uncertainty analysis, we conducted a study to show the importance of the sigma value that the user can enter and its impact on the percentiles result. So you can see here, the first step is to choose the location. We decided to choose a location in a coastal region, and this region will have a combination of factors such as the that will impact the weather, the ocean, the climate also will be a source of uncertainties. So we selected also a suitable system capacity, and we decided to have a comparison study between two different models. So we have the model A with a TMY-A we also selected a standard deviation of 10%, and the results are for the P15, 84.3 gigawatt hour, and the P19, 73.5 gigawatt hour. So the comparison will be based on these two values. And the second case that we take, which is the model B, that have a TMY B with the different global irradiation and a standard deviation of 4.6%. So since we have a lower irradiation, we'll have a P50 lower than the TMY A, and the P50 is 79.7 and the P90 is 75. So good models have lowest possible uncertainty, and this sample will show it. So assuming that the solar resources estimate from two different models follow a normal distribution, so the most expected value will be the P50, and its uncertainty will determine the position of the center and also the width of the curve respectively. So the value exceeded with 90% probability, which is the P19, can be calculated and identified in the probability distribution as well. So in the sample below, it's showing that the P50 value provided by the model B is lower than the model A, and the difference of uncertainty here in the model A, we have 10%. So in terms of this uncertainty, we can see that the model B is providing more favorable financial condition, since its P90 value is still higher than the one that have a P50 higher at first. So so this is the result of the analysis. So as a discussion and result discussion, so we can deduce that with a lower sigma, the narrower the GOS will be, and the good model has a low sigma and uncertainty value. So incorporating uncertainty into the energy yield calculation allows for a more comprehensive risk assessment in the solar energy project by considering uncertainties in the meteorological data, equipment performance, and long-term degradation. So project developers can gain insight into the potential variation in the energy production. So this is helpful to identify potential risk and their impact on the project performance. So by understanding the importance of the uncertainty and quantifying the uncertainty in the energy yield, the calculation enables the project developers to optimize system design and performance. So by analyzing also the sensitivity of the energy yield estimates to different parameters such as solar irradiance, temperature, module efficiency, and inverter efficiency, developers can identify key factors that significantly impact the energy production, and this information will allow them to have an informed decision on selecting reliable equipment and optimizing the design. So in the financial consideration, also the energy yield uncertainty has an implication on the project economics and financial viability. By incorporating uncertainty into the financial model, stakeholder can better assess the project economic feasibility and potential risks. So the range of energy yield estimate at different confidence level, the P99, P95, P90, and P75 will provide insight into the potential revenue variation and financial contingency that need to be considered. So as a summary here, incorporating uncertainty into the energy yield calculation through the tool, through pvDesign as a tool, will enable the stakeholders to conduct comprehensive risk assessment, optimize system design and performance, and make informed financial decision. So as a conclusion for today's webinar, we showed the importance of understanding the p-values, the uncertainties in the context of PV design. We have explored how p-values such as P50 and P90 provide valuable insight into the expected energy yield, and by incorporating the probabilistic analysis, pvDesign enables the user to account for the uncertainty arising from factors such as the weather, the equipment, the degradation. So now we can have a Q&A session. If you have any question, I will wait for 1 or 2 minutes for the attendees to write the question. Thank you, and I hope it was helpful for you. So let's answer the first question that we have. So where do we get the standard deviation? So standard deviation here, the value, you can have it either from, it depends on which uncertainty you have to enter, but if it's from the meteorological data, you can contact the source, the meteo data source that you have. Also for the equipment, you need to contact the your manufacturer to have the uncertainty, and based on that value, you can enter the percentage in in pvDesign in the simulation section. Okay. So we have another question, which is what is the most commonly used p-value to assess a PV plant construction permit and secure funding? Okay, so if we are talking about financial evaluation, P90 investor rely often on the P90 estimates to evaluate the financial viability of solar projects. The conservative nature of the P19 helps to ensure the project energy generation and to have a sufficient value to cover the debt obligation, loan, and it provides more caution outlook. But also the P15 is used, but for baseline expectation. So you can consider both P90 and P15. Stakeholders can have a more comprehensive understanding on the potential of the energy outcomes. Okay, let's wait for another question. So who does sum up all influences on total uncertainty as by the formula you showed the user? So let's go back to the formula here. So the U total, which is the uncertainty total, here U model, U simulation, and the U enter annual. So in pvDesign, the standard deviation that we enter already have this formula calculated. So when you enter the enter annual the interannual variability, it's not only one uncertainty, but it's all the uncertainty englobed there. So if you change this percentage, it will impact all the other uncertainties. Do we have any other question here? Let me see. Okay, so we have another question, which is, does the bifacial PV models affect the uncertainty? So the bifacial PV models can affect the uncertainty in the energy yield estimate. So it will affect also the energy production. So bifacial PV models have the ability to capture sunlight from both front and back side. So it will allow to generate additional energy. So compared to the monofacial modules, it will increase the energy production, and it will have P50 higher than the other type of models. It also have an impact with the albedo variation. Bifacial modules benefit from the reflection of the sunlight, which is known as the albedo. However, this value depends on the specific site characteristics, and the uncertainties may arise from this factor. Also, we can include the shading and the angle dependencies and the backside irradiance modeling. Okay, so we have another question. I have never used the result of the energy yield in P50, P75, and P19 appears after only unique simulation. So in pvDesign, you have a limited number of simulation per project. So each time you are changing a parameter, you can clone your design, change, and generate each time a new design. And with each new simulation, you will have the values, the percentiles of probabilistic percentiles in the energy yield report and in the energy yield results each time. So so this one already answered. Okay, so questions are a bit similar, but I'm going to answer again to this one. For the founders and the financial part of the P90, they from the banks, they considered the P19, they rely on the P19, but also P15 can be considered to help them to make an informed decision. But basically, for the financial, P19 will be the valuable that helps to ensure the project's energy generation to cover all the debt. So if we are talking in the financial evaluation, P19 are the one which is most used. Okay. So I think we don't have any more question here. We can still wait for another question. Okay. Send it, and how do we ask for it? So do the manufacturer provide such information, standard deviation, and how? So it depends. So the manufacturer can give you like the efficiency of the equipment that you have. It can give you also the degradation, yearly degradation, and with all the values that you have, you can have the percentage, the user can have the percentage of the uncertainty of the exact value. Also for the weather data, there are some formulas based on all the document and data from the weather. And based on that, you can calculate your uncertainty and after come up with the standard deviation that you can enter. Okay, so okay, we have another question. So why do we take 3% as a default uncertainty? So this value can be changed by a user. It's not a recommended value, but it is a value that is said to be changed. This value is based on the PVsyst value, which is for some sources, some meteo sources. But for example, if we take meteo norm as a source, it gives you the exact uncertainty. So you need to see the source, and from that source you can have the uncertainty. So that value can be changed. It should not always be 3%. You can change it. Okay. Do we have any extra questions? I think we have more questions. Let's see. So is there a standard that defines those percentiles for PV? The p-values generally are based on the TMY and the meteorological data that you enter and the standard deviation for the uncertainty that you enter. So based on these two input of the user, you will have that percentiles calculated directly for you in pvDesign. I think we don't have any more questions. So thank you everyone for attending this webinar. If you have any additional question that you need answer about how pvDesign is calculating the percentiles, you can send us your question and we will answer as soon as possible. So thank you everyone for attending, and I hope it was a helpful session. Thank you.